Hey everyone. Smaller group today. We'll give it a minute or two, see who joins.
Good morning.
Good morning.
Good morning. Jonathan's outside enjoying the post-storm weather. You can't hear yet. So how is everyone doing? Still
Like
holding?
you, 538, way too much.
Yeah, me too.
This is Gloria. I'm doing fine, and I'm gonna miss these Friday mornings.
Good.
Me too.
Hey, I'm glad you've enjoyed it. We'll have more next semester. They'll be a little bit different, and I'll describe that in a little bit.
So I have a question.
Yeah.
I'm about to start. We have
Yeah,
this-
it's so strange.
Yeah, we have like we split it from the normal 14 weeks to a 10-week followed by a 4-week, so that I guess the logic was that if the students have to either send them all home, at least they haven't lost everything. And as it turns out, it looks like they're actually going to be here at least through Thanksgiving. But any words of wisdom for somebody who's about to start?
Well, you'll have my undivided attention since, everyone's finishing and you're just starting. So any questions or problems, I'll be able to get back to you pretty quickly. Words of wisdom, I don't know. Does anyone have any words of wisdom going into lab 1? Seems like ancient history at this point, but
yeah, I think I'm going to start with some of my on-campus labs because my assumption is that they're not going to come back after Thanksgiving.
Yeah, and maybe one word of wisdom with these labs is it does take time to acquire the data. The nice thing is CTIO is back online, and so you're starting with more telescopes than anyone else who started this semester. But still, it does take time to acquire the data. Some of the labs assume a week time scale. For the lab 3 stuff, we assume 2 weeks. So you could probably get by with 1 if you're lucky. And since this is compressed, you may want to put some thought and care into making sure they get their data submitted well enough in advance.
Yeah, my thought was to have them submit all their data for the last 2 weeks, all the observations the last 2 weeks before Thanksgiving break.
Okay. Yeah.
That would give them all of Thanksgiving to work on to have it. Oh, and I'm also doing another 4 weeks in January. So I'm doing 2 back to back.
Okay. And I don't know if you'll do all the labs or not, given the compressed time scale. You'll have to see what works.
They all fit. They should all fit.
They should. I've done a summer session where it's like 5 weeks and we got them all in where they're doing essentially, there's maybe 4 weeks, but they're doing like 2 labs a week or 2 meetings a week, and some of the labs are 2-week labs. And we make it work. We just got to be extra careful to get the observations in time.
Yeah.
All right.
My wisdom would be to make sure that you, even though Dan has at the beginning of each lab these warnings about make sure you save often and don't have any weird names in the file, weird characters in the file names. You cannot say it often enough, because I still had students who were losing work because they did not hit save or submit rather.
Yep, this came up for us just this past week. Well, with lab 4, when they first had to do scientific notation. So if they miscode it, it looks like no response was submitted. And then they say, WebAssign lost my work, and blame it on them. And it's, when you're in that situation, you just don't know really. There are logs that you can sometimes consult. My experience is, I don't know, maybe WebAssign has on occasion, but it could also just be a student who's lying or user error. It's really difficult. You can go conspiratorial on it or whatnot. For the scientific notation thing, I'm going to put a note in the lab the first time they have to submit scientific notation. That's one of the comments I got back. And maybe I should do the same thing the first time they submit a file. All these warnings, I should probably put them in the first time they have to do them.
Yeah, what I've sometimes done in the past with Canvas is had like some really stupid little quiz that they have to fill out. And like, where they have to write things in sign notation that's obvious what it is. And if it doesn't submit, then they know it. And then they have no excuse the next time.
And another thing is, and maybe I'll build this into the instructions. Tell them they should log out and log back in and see if everything looks right before submitting. I normally put that in the syllabus, but maybe I should write it directly in the lab so your students benefit from that warning as well. You know, if it's in my syllabus, your students don't see that. And that's the safest way. And then the onus is on them. It's like, well, did you log out and back in and check? Because if they did, they would have seen these things. All right.
Well, thanks.
Sure. Our pleasure to help. Okay, so let's see, I have a handful of announcements, then we'll go through this lab, which is a little different from the others, but I kind of like it. Let's see, first up we have surveys. I met with the education research team yesterday. Was it yesterday? No, 2 days ago in the evening, because some are in Australia and they're scattered all over the world. So it's always early evening. And we're getting ready for the next round of surveys. There's surveys always at the beginning and end of the semesters, and it's a big chunk of what your participant compensation's for. And there'll be 3 surveys this time. The same survey that you gave your students before, which was on attitudes and self-efficacy and career intentions and that kind of stuff. You'll need to give it again. And I'll send this out, a reminder to you all. I have a larger listserv for people who are doing this who aren't, doing the curriculum but aren't participating in the training this semester. So you may see it a couple times, but we'll send you links for that. And it's really important that we get the same students who did answer it last time. I think we got a reasonable response rate. I think we got about 500 answers back. But if we get 500 this time, great, but it has to be the same 500 students for us to do the pre-post comparison. If others submit it and they didn't do the pre, that's fine, that's good. And we're always looking for ways to improve, response rates. And in fact, I think in the survey that you as instructors will get, which I'll mention in a second, we're asking for your experiences and comments and feedback there to try to help boost response rates across the board. But there'll be the post survey. There'll be another survey, content knowledge, which we didn't distribute earlier because we didn't have it. We had something, but I didn't like it. And so as soon as I'm done shooting the lab 8 videos, I've shot all the way up through lab 7 now, so that's good to go. I'll do lab 8 this weekend and I'll be caught up. These are the overview videos. I'm going to get to work on the content knowledge survey. I want it to be really specific to this curriculum. So there'll be 3 questions tied to each unit. And also that makes it easy because in the surveys, we're going to figure out which units you've done with your students. And so we can see which parts of the content knowledge survey they should do well on. So that will be generated over the next 2 weeks, and you'll be able to distribute it to your students with the other one. So they'll have 2 surveys now. And then there'll be a survey for instructors. And whether you're using OPIS now or not yet, as long as you're teaching some intro astro students, we do want you to fill it out. And even if you're not teaching anyone yet, there's some questions at the top about your experience with this weekly training program. And it's important that you fill that stuff out because that's how we're going to know to pay you come this summer. We have a fall session, we have a spring session that I'll get to in a little bit that's a little bit different. But every, twice a year, you'll have to fill out at least the top part of this instructor survey. So we know what your compensation will be. And that's paid out early in the summer. Okay, so those are the surveys. So keep an eye out for that. all that should be ready in 2 weeks' time. I've created a feedback document. I should have done this at the beginning, but I didn't think to do it till now. Let me, let's see, I have it. Maybe I'll share my screen to show you the current sorry state of it. Let's see, you're all over here. Spread you out a little bit so I can see you all. And so, and let me copy this and I'll put it in the chat, but I'll also mail it to you. Along with a few other things like the grading guide, which I have not updated for the semester, but that'll be my next thing to do. And the supply list for purchasing the parts for labs 2 and 8 and the protractors and stuff like that. Anyway, this is here, and it's pretty simple, just general comments, and then it's broken down by each lab. And the stuff that you've said so far, I took quick notes. I just threw them in here this morning. They're really brief, and feel free that if it's your comment that I've represented here to go and elaborate on it, to add other comments. And my plan is to do another pass once we get through the survey stuff. In November and December, I'll do another pass to the labs, try to incorporate. I can't promise we'll incorporate everything, but we'll consider everything very carefully and weigh the pros and cons. You know, a lot of ideas are good ideas, though in practice it may not work out, or maybe it'd be good for your students, but not for general students. So we will think about everything with the goal of incorporating as much as reasonably possible. And my programmers have already started having some discussions on some aspects of things that we've talked about before. But yeah, flesh out this feedback document best you can. But you know, whatever it is fine. The spring semester is really about feedback. Get to that in a second. That document's ready and hopefully gets bigger and smaller, right? You put things in and I do them and take them out. Next announcement, many of you know Kate Meredith. She is director of Geneva Lake Astrophysics and STEAM, which used to be the education group embedded in Yerkes Observatory. When Yerkes closed, they got a place nearby and set up shop, and they're hoping to get back into Yerkes as that works itself out. But she's been part of all of our grants, all of our education grants, some in major ways, some of our education grant. What she does is accessibility, blind and visually impaired students and deaf and hard of hearing students. The BVI and DHH are the acronyms. And we try to build her into all of our grants. And some of the grants are all about accessibility. The one we just put in about a month ago, it's very accessibility focused. And sometimes it's very small. And this grant is kind of small. There's $36,000 budgeted for glass, and they're going to do a number of things. They haven't started yet, but they will be beginning now. They're going to go through the curricular materials and evaluate their accessibility for these two groups of users. Like for BVI, we've done things already. Skynet, the web interface, Afterglow, the web interface, they're compatible with screen readers. Some of the stuff has been built to be more useful for blind students, like some graphical interfaces. You may not have seen it, but they're tab and text alternatives, like the Sky Viewer, where you can navigate the little planetarium thing in Skynet. There's an alternative version with lists that a screen reader can read. But not everything works for blind and visually impaired students yet. And with that small of a budget, it'd be too ambitious to say we're going to make the labs work completely for BVI and DHH students. Instead, she'll be doing a review of all the materials, figuring out what works, what doesn't, and making some suggestions of things that can be changed on the budget, and identifying the things that won't work and maybe what some alternatives may be. That's part of what she's doing. Another part is if you have a BVI or DHH student over the next 5 years, she will work individually with you and with the student to get the most out of the curriculum as possible. And she will also put together and not just she, but the team at Glass. There's a number of people there. It's not just her. Put together a document for your disability services entity on campus. Whatever they are, this is the entity that people with these disabilities interact with. And we're going to put together a few pages of description of what this curriculum can and can't do for them. And they'll interact with students. And you may have a blind student want to do astronomy, or a deaf and hard of hearing student decide to take it on. And I encourage you to recruit, may be too strong of a word, but if we can have a handful of these students over the 5 years, maybe not in the spring semester. If it happens in the spring, fine. But in the spring semester is when she's going to be doing the evaluation and really understanding what we can and can't do easily. But after that, in the last 4 years, we would like to have a few of these students, in part to go back for more money. But also, I learned just yesterday, I can go back within the confines of this grant without having to do another grant. I can go back to NSF and say, hey, we've done the promised review of the material. We've interacted with a few students already. Here's our first annual report. We've been doing great things. We would like to have a discussion with you, program officer, about bringing in an extra whatever, $100,000, something like that, to really ramp up the accessibility of the materials. And I know most of you have no experience or little experience working with people in these categories, but because Kate's on board, she'll make it as easy as possible. Anyway, enough with that pitch. You kind of get the idea. Be on the lookout for these people and try to recruit them if possible. And again, it's mostly going to be through the disability services entity on your campus, and we'll get that material ready over the next few months. And last announcement, and I'll pause for comments and to take a breath, I guess. So next semester, what is this going to look like? So this semester, we tried to do these meetings as early as possible to try to stay ahead of when you may be implementing. I think it worked for everyone except NC State. They were on schedule for the first half, but when we took our little week break, they got ahead of us. Though they're not participating in this, they've done it many times before, just not with the updates. Anyway, so I think it's worked out okay. In the spring semester, we're going to delay these as much as possible. The idea is we want as many people to go through beginnings of an implementation process. And next time, it'll be for people who have been using the labs forever that aren't here right now. We're going to encourage them to join in, and people who are implementing for the first time. And if you're here learning this stuff, but you're not going to implement until later, you probably don't participate next semester. You're welcome to attend if you want. But we really want you to do one semester learning the material, one semester after your implementation. And that would be about, okay, I did it, and this is what didn't work for me. What am I doing wrong, or what can you guys change to make it go more smoothly for my students? And you have all sorts of different students. Some of you are at Research One, some of you at small institutions, community colleges. So we're going to get a mix of things, and it'll be much less about me talking the whole time, presenting a lab real quickly, presenting an hour and 50-minute lab in the 30 minutes I leave for myself after announcements and discussion. So it's going to be about you all telling me stuff instead of me telling you stuff. And we want to be proactive. We want to know this stuff. That's the plan. So I'll pause. Comments about any of that? Okay. So let's dive into lab 8, our final lab. I think I have it here. So again, I haven't updated the instructions at the top. I have for all the other labs, and I will for this lab this weekend once I shoot the new overview videos. This one will probably also have an equipment video. So there'll be 4 overview videos, and the introduction, the equipment, background, and procedure, where the other 3 are standard if you've been following along. And I think I mentioned this last time. If not, I'm sorry to sound like a braggart, but people are using these videos. I checked the analytics and we're getting 400 hits a day, and it's up to 34 hours of watching every 24 hours. So whether it's the tutorial videos embedded in the labs, it's mostly those, or the overview videos at the top, they are being used pretty broadly. And once we have these overview videos, they're essentially what an instructor would present. So depending on what you're doing, for some of you, you're your own instructor and you're going to present what you want the way you want. I respect that. But some of you are at large institutions and you have a bunch of grad students delivering the labs like I do here. And then you have to decide. Sometimes maybe it's better that they are doing a presentation so they hone their own teaching skills, or maybe you just want to make use of my videos as the instruction and the TAs become more supplemental to help troubleshoot technology problems, to answer questions in forums, not be responsible for the overview. Totally up to you, but the videos seem to be being used. And also probably you'll have, after implementing, you may have feedback from me on ways I can improve them. Anyway, that was an aside, but by the end of this weekend or shortly into next week, all this will be updated to look like the other stuff. Now, Hubble's law, instead of going straight to goals, let me get a figure down here in the back, one of the background sections. This is, again, we've seen this before. This is our simplified cosmic distance ladder, starting on Earth scales down here in Lab 2. So, of course, we must end up with Hubble's law. This course has been organized around the cosmic distance ladder. This is the top of the cosmic distance ladder. So we have to have a Hubble's law lab. That's one reason to have it. Another reason is we've thrown in a few labs to cure, or to attempt to cure or correct misconceptions, common big misconceptions. Labs 2 and Labs 8, both at the bottom and the top of the cosmic distance ladder, are designed with that intent as well. At the bottom, why is it hotter in summer, colder in winter? The standard misconception that we all have to clarify in first semester astronomy courses. Then on the other end, we have the nature of the expansion, which most people don't understand. Many instructors don't understand, and I'm sure you all are not in that group, but maybe some of your TAs are. And so you want to get them on the right page before they instruct the students. And so this will not use Skynet. And so it's also like Lab 2, we're not using Skynet. We thought about what is the best way to cure the misconception. The misconception is that in the beginning, space was this vast empty void and all the matter and energy was here, and then boom, when it expanded out into the void. And that's not what happened. It's what the name suggests, and which leads, contributes to the misconception. Big Bang sounds like an explosion of matter into space, matter and energy. And of course, the name was introduced by steady state advocates in the 60s to diminish and be derogatory towards this theory. They didn't like it, but the name stuck, and it's confusing. Cosmos. The reboot of Cosmos came out a few years ago. There have been a few iterations, but in the first episode, he redoes the cosmic calendar, beginning with the Big Bang. And I love the series, but even there, Neil deGrasse Tyson depicts it as boom, an explosion in space. But it's hard to depict correctly. Anyway, this lab is designed to correct that misconception. And there will be a 9th lab. We got funding through a separate grant, a gravitational wave research grant, to build a 9th grant that would build off of this. Here they're going to learn what the nature of Hubble's expansion is. They're going to make measurements with rubber bands to reproduce Hubble's laws under different scenarios. And there'll be a 9th lab using gravitational wave events to measure Hubble's constant using standard sirens instead of standard candles. Particularly since Skynet was the first to discover, co-discover, there were 6 groups that did it simultaneously, discover the first optical counterpart to a gravitational wave event. These can be used to measure Hubble's constant skipping the entire cosmic distance ladder. It's a check on the cosmic distance ladder. So the idea is lab 8 will set up the concept, and then lab 9, they'll actually measure it astronomically. And of course, it's becoming a lot of labs. You may choose not to do all of them, but that's kind of the idea. There will be another lab after this.
Question, Dan,
Yeah,
will,
go ahead.
will they actually take data for Lab 9?
So-
Or is that going to be like a archival data thing? I would assume, I don't know.
We're trying to figure it out. So far, there's only been one of these events. And I love the idea that, I think it was Jonathan who came up with it back in lab 5 for the supernova. Instead of it being that one supernova, we just keep refreshing it with the most recent thing to come off the prompt telescopes. And we just got $500,000 to chase these gravitational wave events. So as things improve in the future, hopefully we'll have more and more of them instead of just the one that we got back in 2017. It wasn't announced to 2018, but still. We may write it initially to just use that one. And there are different ways we can do it. We could do a fully archival way where, you need the distance and you need the redshift, right, to get Hubble's law. The distance would be from a standard siren. So we might do something like in lab 3, where they did chi by eye orbit modeling, and we may do chi by eye gravitational wave strain modeling. So they get the masses and things like that. And we'll build that in as another option in the graphing tool. And then that gives them the distance, and then you need the redshift, and redshifts are the easiest thing to get. But the challenge with the gravitational wave thing is, which galaxy was it? Because the localization region was huge. There are 50 galaxies in there. So one approach we can take is, here are the 50 galaxies we shot, and here are the 50 pre-images, because we shoot the same galaxies over and over as part of this supernova program. Find it. And they have to go through all the archival data to figure out which one it was, and then they can look up the redshift of that galaxy. That's a no observing approach. Another one is we say, okay, it was this galaxy out of the, I think it was 50 of them actually. But which source is it? Go back and image this galaxy, and so you get a picture of it without the kilonova in there, but they could also pull that up archivally. Another possibility is we're building a spectrograph into Skynet, though I'm not sure if they would be able to get the redshift of this galaxy in a short amount of time. That's the key thing for the OPIS curriculum, short amount of time. That's something we'll consider as well. So it's open-ended. Maybe they'll acquire an optical spectrum if we can make that work. And they've already learned how to deal with the radio spectrum, so it would make the graphing interface pretty much the same. They measure the redshift of the absorption line in this case, and go from there. So different possibilities are still on the table. And we'll develop it next year, maybe in the spring.
Cool, thanks.
Sure, yeah, it should be exciting. And multi-messenger astronomy is the new thing. Anyway, this would set that up. It would teach them what Hubble's law is all about. So I think that's enough here. Let's just go back to the goals. Oh, I should point out this lab, like lab 1, is in 2 questions. In lab 1, it's convenient because it's really kind of 2 weeks. Question 1 in week 1, question 2 in week 2. Here, it's simply because we could not fit it all in one question. WebAssign has a limit of how much stuff, and it didn't quite fit. So there's the final activity is separate. Just something you got to be aware of so the students don't forget to do it. Okay. Goals. 1, this is my phrase. It's not the most, I like it. It rolls off the tongue, though it could be a little bit more specific, but learn that the Big Bang was not an explosion in space, but an explosion of space. That's really not an explosion of space. It's a rapid expansion of space, but you can kind of describe that's what an explosion is, a rapid expansion of something. But anyway, I lean into it. You may like it or not like it. I don't know. 2, we're going to determine that our galaxy is not at the center of the universe, and the universe, in fact, has no measurable center. And this is something you have to emphasize. Once they build a Hubble's law, you'll see everything's moving away from us. And it makes you feel like, hey, we're at the center of things. But you can do the same experiment from any other galaxy, and the way we've set this up, they can easily hop to another galaxy and reproduce the experiment, and they still get the same Hubble's law. Everything's moving away from everyone. So everyone could accidentally think they're at the center, and it just shows there is no unique center. And the title here is The Galaxy's Place in the Universe, Part 2. Part 1 was the second part of the Great Debate in Lab 6, showing that the Milky Way is not unique. We're one of countless galaxies. Here, we're specifically talking about our location in the universe and it not being special, which again is very much the theme of this course. And the theme of introductory astronomy, you can organize it around this idea that we keep thinking we're special and we keep learning we're not, over and over and over again. At least not in terms of location in universe. You know, being conscious entities is pretty special, though, and no one knows that question, of course. That's the big question. But personally, I imagine that's a property of the universe writ large as well. But get into philosophy and religion there. Let's see. Determine whether the universe is expanding at a decelerating, constant, or accelerating rate. Basically, using the rubber band and the procedure I'll show you, they can simulate all sorts of different types of universes. And so this can tie into dark energy. The last lab tied just a little bit into dark matter. That was the carrot. This lab will tie just a little bit into dark energy. So another carrot. Okay, here's the equipment that they need to come up with. The rubber band. And again, I forget if I said this to you or if I was saying this to my TAs. I apologize if I'm repeating, but it has to be the right kind of rubber band. Can't be too small. Did I say all that to you? Yes, I did. Okay, thanks. Yeah, they have to find it. And it's pretty standard. It's not like a rare rubber band, but there are lots of rubber bands that don't work as well. Now, if you're doing it on campus, you just provide it. You buy a bag of these, and we provided you with the link in the supplies document. Otherwise, scissors, ruler, it has to have centimeters on it. One student over the summer got confused and thought we were doing inches. So that student had to stretch the rubber band out 2.5 times as much and had all sorts of snapping problems, but centimeters. Marker, foam board or thick cardboard or bulletin board, any of that works. And push pins. I think they were labeled as tacks previously, but someone corrected my terminology. They're push pins. Okay. Inexpensive stuff. It's not hard to get. And we're just going to assume the students can find it this semester, but in the future, you'll provide it for the students. Okay, 2 background sections. One on the true nature of the expansion in Hubble's law, where we'll show it's not a Doppler shift. In the last lab, they learned about Doppler shifts, and part of that was to compare and contrast to the expansion of the universe. Often when we make our Hubble law plots, we're assuming it's a Doppler motion, a motion through space. But that's not what's going on. So we're going to argue that case in this section. And then the next section is, well, if it's not a Doppler shift, what kind of redshift is it? And we introduce the idea of cosmological redshift. So this is the part where they have to bend their mind a little bit and unlearn what you have learned, as Yoda would say, and learn things differently. So this is a little bit of a capstone in some sense. In Lab 5, we learned about measuring distances using Cepheids for nearby stars and type 1As for faraway stars. Again, distances are the hard things to measure in astronomy. In Lab 7, we learned about the Doppler effect. So, measuring redshifts from a spectrum and how to interpret them as a motion through space. If they are a motion through space, how to take that redshift and turn it into a velocity. The redshift is right here. It's just change in wavelength divided by emitted wavelength. And that gives you the thing called the redshift. But if it's a motion through space, you then multiply by c. As long as it's a low redshift, less than 1, this is the proper equation. And that gives you its Doppler speed if it were moving through space. And you do this for a whole bunch of galaxies. And here we plot distance on the x-axis. And I'm always careful to say apparent recessional velocity on the y-axis because it's not really a Doppler effect, as we'll see. It appears as one because it's just a redshift. You're measuring a redshift, and then you have to assume, is this a Doppler redshift? Is it a cosmological redshift? Is it a gravitational redshift? And you never really know. It's always context specific. If you interpret it as Doppler, then this is recessional. So I say apparent recessional. And we see the farther away things are, the faster they're moving from us. And there's a little bit of scatter, and that scatter is internal, it's local gravitational attractions. Like this galaxy is pulled towards this one. And so you get a little bit of scatter, but there's this overall trend on large scales. Once you get out beyond Andromeda, this is what dominates. And think about things that are farther away moving apart faster. If you run the clock backwards, they'd come back at you faster. And everything in this plot kind of lands on the same spot of space at the same time, a certain time ago. And it's given by the inverse of the slope of this line. The slope of this line is, the units are kilometers per second per megaparsec, which is a confusing unit to students. We've all gotten used to it for Hubble's constant, but it's really inverse time. Kilometers, megaparsecs, they cancel their distances. So it's inverse time. The inverse of this is time, and it's the age of the universe if there are no accelerations or decelerations, which is 13.8. I need to update this number to the most recent measurement. And there have been decelerations and accelerations, but they mostly kind of cancel and you still get something close to 13.8. Anyway, so if you view this as an explosion from a point in space, it's a weird kind of explosion where the outer shells are moving faster, the inner shells are moving slower. That's kind of a strange explosion. Normally, if you have an explosion, there's an expanding shell. There may be a Gaussian distribution of velocity so that the shell may spread a little bit. This would be a very unusual kind of explosion. That aside, there are a couple arguments that you can make that this can't be the case, can't be an explosion. If there's an explosion, there's a center and an edge because the matter can only travel so fast. So there's going to be a region beyond that outermost shell where there's nothing. And it'd be centered on the center of the explosion. And you would probably be somewhere out in these outer shells. So if you look out, you'd see certainly a region out beyond with nothing, and maybe a region interior with nothing as well if you expand it as a shell. And we look out and we don't see that. We see a uniform distribution of galaxies all the way out. Now the figures, this is a galaxy redshift survey, 2 slices, and it's they're a little confusing. You got to put a little bit of time into this because they look in the edges and they say, yeah, it's dropping off in the edges. Well, that's because those galaxies are faint and hard to see. So we're only seeing the most luminous. It's what we call an observational selection effect. We understand our observational selection effects. Once we correct for it, there's really no lower density of galaxies out there. Density of galaxies seems to be the same everywhere we look, nearby, far away. They do clump on small scales due to gravity, but on large scales, hundreds of megaparsecs, they're uniform. So that doesn't look like an explosion. I don't see any center. We don't see any center. We don't see any edges. Back in this is called the cosmological principle, that there's no center, no edge. And back in the 60s, this just had to be assumed, and then they would proceed with the development of cosmology. But now it's observed, no center, no edge. So not like an explosion.
I have a quick question about that graph, Dan. You notice that the ones farther away seem to be tapering off. How do we infer that they are in fact not tapering off?
So we understand the sensitivity of our instrument, and from looking at the galaxies nearby, you figure out how many are luminous and how many are not so luminous. And assuming that luminosity function kind of holds, then you can imagine that same distribution of luminous and non-luminous galaxies far away. Well, we wouldn't be able to see the non-luminous ones, but we can still see the very luminous ones.
I see, I got it. So it matches what we would expect if it were our data matches what we would expect if it were uniform. Got it.
Yeah,
Okay,
yeah, we're
cool.
losing the low luminosity ones, but we understand the brightness limit of our instrument, and so we can correct for it. And
Nice.
it's
Thank you.
beyond what the students can do, but you can explain it to them and say, we've checked this out, and once you correct for this, it is indeed uniform.
Cool.
There's
Thank you.
certainly not a hard edge either. Even though it's dropping off, there's no solid edge, like edge of the expansion. And also, we likely wouldn't be at the center. We'd be flying with the material off in the edges. So you'd see, something different than this. And here's another one. And this one involves a little white lie that I decide to use and I get away with. I've never been called on it before. But I also put in the technically correct explanation. So if you're uncomfortable telling the white lie at the survey level, go ahead. And I'm trying to remember my postdoc who used to teach intro astro. He'd always start the semester off by saying, this semester you'll be presented with 3 different types of lies. I can't remember all 3. One are like honest mistakes on his part. One are lies that we tell to make it simpler so you can understand it. And then if you keep going on, we'll correct these lies. I forgot the 3rd category, but it's kind of a brilliant way to introduce, to set the students up. Anyway, what's my white lie here? This is the Hubble Deep Field. I've circled the galaxies with redshifts greater than 1. There are many of them, of course, but they've labeled the redshifts on a handful of galaxies. In this image, I circled the ones with redshifts greater than 1. If we were to take this Doppler shift equation, which they learned in lesson 7, redshift greater than 1 would mean a recessional speed greater than c, which is not possible. You can't travel faster than the speed of light. That's another reason this can't be an explosion. And we see some things that would be breaking the speed limit. Now, it's a white lie because this equation actually does not hold as the redshifts approach 1. There, you need to use the relativistic Doppler equation. And what that one instead shows that as you have redshifts, if you have redshifts greater than 1, it doesn't mean you're going faster than the speed of light, it means you're going close to the speed of light. As the redshifts get higher and higher, it means you're getting closer and closer. So if you were to replace this with the correct relativistic Doppler equation, which is beyond survey level students, that would be the conclusion. Not that, hey, look, these galaxies appear to be traveling faster than the speed of light if we interpret this as a Doppler shift, but instead they'd be moving near the speed of light. Now, if they're moving near the speed of light, you would have special relativistic effects. Time would slow down, the mass would increase, and these are things we would see in these galaxies. We'd see temporal motions like pulsations of stars going slower. We'd get the wrong masses, and we don't see any of that stuff. There are no special relativistic effects. So even if you use the relativistic Doppler equation, because we don't see the special relativity, it's still not right. Again, that's a little bit above the survey level, but I have it here in a technically paragraph, just in case you have that one student who speaks up. It's never happened to me, but if you have that student, let me know. I'm curious and definitely recruit them to become a physicist. So how can we explain this? If it's not an explosion in space, how do we explain it? Well, Einstein showed in his general relativity that space itself can move. It's not emptiness, it's a thing. If you want to get into a little bit of GR with curved space instead of a Newtonian gravitational force, you have curved space. You can go there if you want. Or maybe if this is coupled with second semester, like Astro 102, I've been calling it material. They've seen some of this. But anyway, Einstein showed the universe itself, the space, can expand. And it can expand at whatever damn well speed it wants to. It's not restricted to the speed of light. And basically, the galaxies go for a ride. And it's kind of depicted here. Here we have the Big Bang. Time is in this direction, so space is expanding with time in the galaxies. They can still move through space due to local gravitational attractions, but they're really just being carried apart from each other. And since space can expand at whatever speed it wants to after the Big Bang, then you can have speeds greater than the speed of light. And it's not a problem. If you start with a uniform distribution, you'll end up with a uniform distribution, so no center, no edge. Now, so that solves the previous problems. Now, they may look at this figure, a couple things. three-dimensional space expanding is hard to visualize. What's it expanding into? So we always depict these things one dimension down. We portray space as two-dimensional, show it expanding in a three-dimensional framework. 3 dimensions expanding into 4, it's hard to envision 4 dimensions. Some people can do it. My college roommate claimed that he could do it, but he was always high when he said that he could. So I'm not sure I believe him. And I use that in class. That's a good joke. And then I follow up with Stephen Hawking said for about 15 minutes in his life, he was able to visualize 4 dimensions. And then I say, what makes you wonder what he was smoking? But anyway, so we go a dimension down here. Now, I don't like this figure, but this is just me. I'm going to go on a little tangent because it has edges, right? And the students say, well, I see edges in this figure. And then you say, well, no, it's just, it would go on forever. It's infinite. And some of them may be happy with that, but I personally don't like physical infinities. If the universe is, and this has nothing to do with the lab, I'll give you a 20-second rant, but if the universe is really infinite, it means that we're all repeated an infinite number of times, that this training session is going on right now an infinite number of times with people who look just like us. And if I were to make a universe, I would deem that to be kind of wasteful. So I don't know. I didn't make this universe, so I can't claim responsibility for how it's designed. But personally, I don't like physical infinities. And Einstein gives the possibility that the space could have some curvature. It could wrap around on itself, something like we see here. This is the classic coins taped to a balloon. You blow up the balloon, all the coins appear to move apart from each other. And it's a way of doing it without infinite space. I just throw that in there because I hate physical infinities. Okay. So consequently, the Big Bang is better described not as an explosion in space, but an explosion of space. But then our second background section, and the parts of the lab go pretty quick. The second background section is, well, if it's not a Doppler redshift, we're still measuring a redshift from these galaxies. What is that redshift? And it's what we call a cosmological redshift. And again, I know you know these things, and I feel I have to say this every time, so I don't feel stupid explaining this stuff to you. But this is how you may present it to your class. And consider light traveling through an expanding universe. Light waves have no internal cohesion. As the universe expands, they get stretched out. Now, the students may wonder if they have internal cohesion, are they expanding with the universe? And the answer is they're not. Hubble's law, the expansion speed, the redshift, it gets bigger with distance. So at small distances, Hubble flow is really inconsequential. And our intermolecular bonds hold us together against the expansion. Gravity holds the Earth together, and the solar system, and the Milky Way galaxy, even the local group. But beyond that, Hubble's law, the Hubble flow dominates and can pull things apart. But we're not expanding with time. And since I used to be really skinny, and my belly's not as skinny anymore, so I can work a good joke in there too. But anyway, let's see what we have here. So light, it has no internal cohesion. So the farther it travels, the more it gets stretched out. And so really Hubble's law is redshift versus distance. That's what we're measuring, the stretching of the light. And it's being stretched not because of a Doppler effect, but because space itself is stretching, and it stretches it out to give us Hubble's law. So this is cosmological redshift, different from Doppler redshift, and top of the cosmic distance ladder, which we've already talked about. So procedure sections. The first one is just the rubber band universe they're going to be using. We're going to have a little universe made of this rubber band. It has to be at least 18 centimeters long when cut. You put one end at 0, and then you draw a galaxy every 3 centimeters. So it's a little section of the three-dimensional universe encompassing 5 galaxies that happen to be uniformly distributed. It's a little contrived, but you get the idea. And we can expand the space and watch how the galaxies are pulled from each other. So they're at 3, 6, 9, 12, and 15 centimeters. And you tack them in. And if the pin is too long, you may have to go over the edge of the table so it stays in. The pin may run into the table. Here is the rubber band at normal resting length. So galaxy 1 at 0 centimeters, galaxy 5 at 15 centimeters. And here it is expanded out to 27, which may be the max, I think. And you can see they get stretched out in this case. And you want to put your tacks in slightly against the rubber band at an opposing angle, else they can pop out and fly across the room. And you know the saying, it's all fun and games until someone loses an eye. Hasn't happened yet. Normally these things are pretty innocuous, but if you're worried, this may be a safety goggle experience. Or until the first person loses an eye, then everyone will be using safety goggles. We've run it for years without problems. Occasionally something pops out and it's kind of exciting, but you may want to seriously think about safety goggles. I don't know. We haven't yet, but it may not be a bad thing to consider. And the way it's going to work is this universe will expand, this one-dimensional segment of the universe, and then we'll pause time because we have godlike powers in this lab. We can pause time, stop, I keep hitting my microphone, stop the lab, make any measurements, and then resume time. And this thing expands like a certain number of centimeters per minute, and they can expand time at an accelerated rate. They don't have to say, okay, to go from minute 6 to 7, here we go. Start timing and slowly expand the rubber band. They can just move it to the next position and freeze time again. This godlike power is a disadvantage you'll see in measuring distances in just a second. Okay, now in the procedure, we're going to measure Hubble's law from galaxy 1. And that's the Hubble's law we would infer. And then we're going to measure it from a different galaxy because, as I mentioned before, Hubble's law gives the appearance that we're at the center. And you don't want to go through this whole semester teaching them we're not at the center, not at the center, not at the center, and come up with Hubble's law. Everything's moving away from us. And damn it, we look like we're at the center. So we're going to repeat the experiment from galaxy 2 and show that they also get the same result. Everything's moving away from them in the same Hubble's law fashion. And then down here, we'll do a decelerating universe and an accelerating universe. Because we used to think the universe was decelerating because, yeah, we don't know what caused the initial expansion, but it's full of matter that's trying to pull itself back together. And the matter follows the space and the space follows the matter. So we thought it would be decelerating. But we'll also do an accelerating one, which turns out to actually be the one we live in. Then we'll look at some type 1a supernova data and tie it to dark energy. That's the carrot. Okay, and the first one goes a little slow because they're learning how to do it. And then as they repeat it, it goes pretty quickly. So what we have here is time in our universe in minutes. So this universe will go from minute 0 to minute 9. And this is the distance between galaxies 1 and 5 at each of these minutes. So they can just jump to these moments in time and freeze them. And they position the rubber band, tack them in with a certain number of centimeters between galaxies 1 and 5. And here you see galaxy 1 is at 0, galaxy 5 is at the prescribed distance away. And then they're going to measure the distance from 1 to 2, 1 to 3, 1 to 4. They don't have to measure 1 to 5 because they use that to set the pin. And they'll do it for all the ones they can. Anything less than 12 centimeters they can't do because the rubber band doesn't compress, it only stretches. So we leave this blank, it'd just be a few data points not in our Hubble's plot, but that's okay. And then we have two special things. We have how far these galaxies are from us now, that's the bottom row, and how far they were from us when the light was emitted. And those are the yellow boxes, at least approximately. So this particular universe, light travels at a particular speed of a certain number of centimeters per minute. Yeah, so it's a fictitious universe, but it has a speed of light represented primarily by this yellow box, a set of yellow boxes. So for each galaxy, we know how far away it was when it emitted the light and how far away it is now. And they'll do stuff with that in a second, but first we just ask them to plot the distance between galaxy 1 and 5 versus time. So not their own measurements, just these first two columns here. And that's just to confirm that this is a constantly expanding universe. So they know what kind of universe we're dealing with. So it should look exactly like this, and they'll just use the simple curve feature in the graphing tool. We ask them, is this a constant expansion? Yes, it's a constant slope. Okay, then they're going to take their d nows, the distance of each galaxy now, and their d thens, and move them down to this table. D thens here, d nows here. They're going to calculate the two things they need for Hubble's law: luminosity distance for the x-axis and cosmological redshift for the red axis, for the vertical axis. And that's everything you need for Hubble's law, and you can get it all from the d nows and d thens, which is super convenient. So distance, well, how far did that light travel? Something longer than d then and something shorter than d now. It was traveling through an expanding universe. Like if the universe didn't expand, it would travel d then to get to us. And if the universe was always as big as it is now, it would travel d now to get to us. So in reality, the light traveled something in between. And there's a fancy, complicated equation for this. It depends on things like omega matter, omega lambda. But for the purpose of this lab, they can just average the two, and it's close enough. Now, this is something called the coordinate distance. This is the distance you would measure between objects with a giant ruler. Again, godlike powers, I can just measure the distance between this galaxy and this galaxy with my giant tape measure. In reality, we don't have those powers, and we instead use standard candles like type 1a supernovae. And we don't measure coordinate distance, ruler distance, we measure luminosity distance from standard candles. And there's a difference. And the difference is that light's coming to us. And since the universe is expanding, that light train, the train of photons, is getting stretched out. And so we receive them at a lower frequency. So we infer the object to be fainter than we otherwise would have, and consequently infer it to be more distant from us. If we see it as fainter, we think it's farther away. That's the difference between luminosity distance and coordinate distance. It has that time factor as well. And the first time I did this lab, I didn't think about that. I had them plot redshift versus coordinate distance, and all the Hubble's laws were curved. And the lab still worked, but it wasn't right. And so we built this in, and it's not ideal. We basically say, okay, take your coordinate distance and multiply by a correction factor. And we explain the source of it, as I just explained to you. And we tell them that correction factor is d now over d then, which is correct. D now over d then is 1 plus z, 1 plus redshift. But we just tell them that's the correction factor to use, and they just have to accept it. Once they do that, they have their luminosity distances, all from the d nows and d thens. A sample calculation goes here. So now they just need the other axis and the redshifts. And redshift is again defined as change in wavelength over wavelength. But if wavelength is scaling with the universe, no internal cohesion, then lambda now is just proportional to d now. Lambda then is proportional to d then. And so we can do these substitutions, and the constant proportionalities cancel. So redshift is also given by d now minus d then over d then. So again, from the d nows and d thens, they can get the redshift too. Sample calculation. And then they go to the graphing website and they plot redshift versus luminosity distance. This is data I collected, being very careful, showing you kind of what you should be able to expect if they're careful. And it's a linear relationship in a constantly expanding universe. And we ask them, Hubble's law states the farther a galaxy is away, the faster it appears to be moving. Have you replicated this? And the answer is yes. It's nice. You get, if you treat it as an explosion, it's a really peculiar kind of explosion. As I said, the outer material moving faster, inner slower. What caused that kind of explosion? But here, just by stretching a rubber band, you get it automatically. So I think that's a powerful message. I'll go a couple minutes over. But now that you know how to make the measurements, this should go quick. Next question, are we at the center? Because you look at this as like, well, we're here and everything's moving away from us. We must be at the center, which again is not the message you want them to walk away with at the end of this sequence. It's the exact opposite of the point, the whole sequence. So we have them do it again, same constant expansion, but everything measured from galaxy 2. So here your d thens, the d nows are in yellow, and they go through the same process, d nows, d thens, except this one here, everything is zeros. And There's a little tutorial on how to graph two curves. There's another feature on the graphing website. See, if we do multiple curves, they all have the same X value, and that's not the case here. In this case, you want to use the dual feature. It's two lines, each with a different set of X's. But pretty straightforward. And so they're going to plot the Hubble's law measured from galaxy 2, and they're going to overplot Hubble's law measured from galaxy 1 that they did before. And you see they line up perfectly. You're missing one galaxy at the edge because you shifted over a little bit. I know that's Dave Moffat who just did the alternate universe, Dan. It's gotta be. He changed his, Dave, is that you? He won't fess up. I know it's Dave.
Maybe not.
Okay, yep. I called that one. Yep. Wearing the evil goatee. When I first was applying for jobs, I was young and looked even younger, and I couldn't grow any facial hair out here. So I actually applied for jobs with the evil goatee. In fact, it wasn't even that good. I couldn't get it to connect here. So it was a mustache and a soul patch as best I could do. I wanted to look older than I did, but
The only reason I have a job at Furman is because I didn't have a ponytail.
that's right. The guy who applied for the
competition had a
job before
ponytail.
you. Yeah. And they decided it based on, hopefully not completely on that, but.
Oh, he had a beer with lunch.
Oh yeah, okay, yeah.
That was evil.
Back then, perhaps. Anyway, so we ask him, do observers in Galaxy 2 have as much right to say they're at the center? Yes. Can anyone claim to be at a unique center of the expansion and hence the center of the universe? No. Okay, last part. They're going to begin by doing a decelerating universe, and they begin by plotting the distance between Galaxy 1 and 5 as a function of time. That's here, the blue curve, it's decelerating, and they overplot the constant acceleration. So they can see, you know, we're expanding faster initially, slower later on, that yes, we are indeed in a decelerating universe. And then they're going to do the same measurements. Again, there's a little region here that they can't measure because the rubber band would have to compress, but they still get plenty of them. And go through the same process and get a Hubble's law. They plot it here in blue, the decelerating expansion, and they overplot their constant rate of expansion Hubble's law from before, and they see that it curves upwards. And this is guaranteed to work because they're measuring this point, and this point. This one's 0. This one's given, right? Where they put position 5 is given with the tack. And all the conclusions you draw are dependent upon that last point being higher. So they can't get it wrong because their measurements may be off for these 3, but it won't be for this one. And so that guarantees this is going to work. They're going to get to the same conclusion. This makes sense because in a decelerating universe, we're expanding faster initially and slowed down to the current rate. So faster initially was a long time ago. That's far away. So go to great luminosity distances, faster expansion. The blue curve is higher. Okay. And we ask them, in a decelerating universe, what happens? It curves up to higher redshifts at large distances. Then they do the accelerating universe. Again, they plot the distance between galaxies 1 and 5 versus time, that's here. And then the constant expansion here. And so they say, yes, indeed, it's an accelerating universe. It takes a while for it to get up to our current speed, the same slope. So expanding slowly initially, and then normal speed here at current time. And this isn't a side note, it's not in the lab, but you know, this accelerating universe is older. It takes longer to ramp up to the current speed. And you know, back in the 90s, before most people accepted dark energy and the cosmological constant, we kept running into this problem. You'd see these news articles that would say, astronomer discovers object older than universe itself, which of course can't be. Nothing can be older than the universe that contains it. But it's because people weren't accepting of dark energy yet. We hadn't seen evidence for it from this type 1a supernovae. So again, the age of the universe based off a constant expansion. As soon as we realize that, yes, indeed, it's an accelerating expansion, the the estimates for the age of the universe got longer, encompassing these objects. I don't bother them with that in this lab. Again, survey students, they don't need to do the intricacies of that history, though that's maybe something you would do, Jonathan, since you take a historical approach.
Yeah, I do that. I make a big point of that.
Yeah.
With them.
So you could tie off of this, even though it's not, that point's not built into the lab, you could build off of it.
Yeah, I give them a plot where my cheat is I do the cosmology for them already. And so I make a Hubble's law plot that Hubble's law is a straight line. And then they all work it out and all is life is good. And then I give them the high redshift Z data and they see a clear curve and they always get it backwards about whether it's accelerating or decelerating.
Yeah, it's always confusing which way, like this looks like an let's see, the blue curve is the red. So continuing on with this accelerating case, you take the D nows, D thens, make a Hubble curve plot. The blue is the accelerating and it bends downwards. And so if you're normally used to thinking distance versus time, it looks like a deceleration compared to the constant case. But yeah,
what I do is I plot it distance and velocity, and then I plot it look back time and velocity.
Yeah.
And then I say, what does that mean? And then I plot it age of the universe minus look back time versus velocity. And then it looks like their high school acceleration graphs.
And even if you don't do it, you can explain it in words. Again, if we're in an accelerating universe, it was slower in the past. The past is great distances. So we go out to great distances, and indeed the blue curve is slower. It's below the constant expansion. So we ask them that question. And then we just give them the type 1a supernovae, which ties back to lab 5. They learned about using type 1a to measure distances. And we give them 3 curves saying this one's the constant. We don't tell them which one is accelerating, decelerating, but they just figured that out. The accelerating is the lower curve, and clearly the data favors the accelerating universe. So what universe do we live in? Accelerating. Research and discuss dark energy. The answer key is just a link to Wikipedia. The answer, of course, is dark energy is that which is making this data do this, right? That is that which is causing this. And we don't have any deeper idea. Some crazy theorists might, but in reality, we have no freaking clue what the dark energy is. At least with the dark matter, we have some ideas. It's machos, but mostly WIMPs, massive compact halo objects, weakly interacting massive particles, mostly the WIMPs created after the Big Bang, even though they haven't been detected directly. There's some evidence of indirect gamma ray emission from their annihilation. Anyway, blah, blah, blah. Dark energy, we have no freaking clue. In fact, if someone wrote that, I'd probably accept it as the answer. And then finally, discuss sources of error. And let's see, the accuracy with which the pins, I don't believe all these, but I'm very generous here. And these are things students often say. So the accuracy with which the pins can be placed, sure, that's valid. The accuracy with which distances can be measured between stretched out dots. So as you stretch the rubber band, the dots also stretch out. Technically, that does make it a little bit harder to measure the center, but not much. The human brain is really good at centroiding. Whether the dot looks like this or like this, we can still find the center pretty accurately. 3, rubber bands stretch differently as they warm up, and repeated stretchings warm them up. I don't believe that at all, but I can't really discount it, and students like that explanation, so I'm generous and throw it in there. And rubber bands don't all stretch uniformly. Yeah, if you had a really cheap ass rubber band, that would probably be the case. If it was like thicker and denser in some parts and weaker in others, it would not stretch uniformly. Maybe that's true to some degree, but I imagine these things are pretty close to uniform. Still, all those are possible sources of error. Then, of course, we have the standard statement that calculation error is not a valid source of error. If your calculations are wrong, you should go back and redo them and ask your instructor for help if necessary. Anyway, that's that lab. It's the end. Again, it does not involve Skynet, but it will be leading to another one that does. And we spent a lot of time playing with rubber bands and making all this work, because there are all sorts of things you try, and the rubber band has to be too large, or speed of light in this universe, the speed of expansion and acceleration. We played with a lot of things, and I'm actually very happy with how it turned out. We'll see if you are, if you decide to do it. But I'll stop there. Questions, comments?
Yeah, I want to, you do a good job of dispelling scientific misconceptions, but I think you have some historical misconceptions that are built in.
Yeah.
And the main thing, of course, is that Hubble didn't really do a lot of the stuff we give him credit for. I know I make a point of emphasizing Slipher, and if you dig up Hubble's paper, he doesn't cite things that he should have. He really blatantly plagiarizes, and there is all this controversy between him and Slipher. If you dig up Slipher's paper, it clearly has the redshifts, but the explanations are totally not the kind of thing we would modernly think now, because it was still based on the idea that the spiral nebulae were part of our own galaxy.
Yeah, and yeah, I was just thinking as you were saying that, you take the historical approach, and this clearly is designed to get into the concepts as smoothly as possible, not really restricted by the history. But a historical supplement to these labs may be interesting. And since you take a historical approach, this is something we should ponder. If you'd be interested in writing like even just half a page on each lab where it's appropriate. And I had received comments before, it'd be good to highlight some of the women scientists who contributed, the spectroscopy and various things, and they would fit in various places in the lab sequence. The only history I did was the Great Debate. And even that, what the students are doing there is not actually what they had done during the Great Debate. It's how you solve the Great Debate. That's my understanding anyway. And so
yeah, I really concentrate on how people found distances, because I have my own bugaboo about that. I love including, women scientists, but only when I include them anyway.
Yeah,
I'm not going to add them in just because they're women. But in astronomy, we have so many fabulous women scientists that you don't have to, right? There's no, Caroline Herschel, did a lot of stuff, and wouldn't have, the distance to Andromeda and anywhere else without the Cepheid variables and Leavitt. And we wouldn't have, lots of other things without that. So it's an interesting thing. It's also interesting that the Harvard Observatory is right across the street from Radcliffe, and that for that reason, traditional women's colleges, the Seven Sisters and them, have always had fabulous astronomy programs. So
consider it as you run. You're going to run through them for the first time, beginning now-ish or pretty soon, and so you'll get a taste for all these labs, more so than what you've seen it just in these sessions, and you'd probably want to adapt them anyway, since you take the historical approach. And I don't think everyone else here does, certainly not to the degree that you do. I've ordered them in kind of a historical order, but I'm glossing over lots of historical details and don't know lots of historical details to the depth that you do. Consider if you'd be willing to do like a half-page supplement or more if you want to each one, and we could package it with it as supplementary material for those who want it. I think that'd be a great addition.
Yeah, I'll think about that.
I don't want to commit you if you're unwilling, but think about it. If you're willing, that'd be great.
Yeah. I might not have time till the summer or something, but yeah.
Sure. Okay.
And I guess, Dan, speaking of history, probably a mention of Humason might also be.
How much what?
A mention of Hummerson, I'm sorry, Hubble's assistant.
Oh,
That may
yeah.
also be useful. Yeah.
Yep.
Yeah, I mean, what you can really give Hubble credit for is finding the distance to Andromeda. I mean, he really solved the great debate. And I would say that's what he did. You know, none of the ideas that, I mean, Hubble's law and so on, these were all things that Lemaitre had already thought of. And so from a theoretical point of view, Lemaitre was way ahead of everybody. And people largely didn't take him seriously because he was a priest and they thought that he had religious motivation.
And thinking here, I'm not sure anywhere in this lab I say Hubble did this. I'm just referring to Hubble's law, which it just
You
because
do
that's what
once.
it's called.
You do once.
Oh, do I once? Okay.
Yeah, you do it once.
Well, I can correct that too.
Yeah, especially, it was measuring the redshifts. He didn't measure redshifts.
Okay.
He
So-
stole Slipher's redshifts.
Okay. Put these things in the comment document. I'm about to do another pass, and I don't want to say things that are blatantly false, and that's part of why we're doing these meetings and this grant to get this better. I was focusing on making it work, but I also want to be historically right. I can't promise that we'll be able to get the whole thing into a historically proper sequence where, well, don't do it this way because that wasn't done till after this, which you do in the next lab. Because often we've chosen the simpler approach for them to do or understand what they're doing. But I don't want to make historical misstatements either.
Yeah, I mean, Inside Out is almost always historical, with the exception of, as you already covered in the Great Debate, galaxies. I mean, otherwise it's refining. I mean, there are refining techniques, but the sort of basic idea of the distance to Andromeda being outside of our galaxy when he's off by a factor of 5, right, was Hubble.
Yeah. Yeah, the Hubble constant was like 500 when he did it, right?
Yeah, it had to do with confusion of Cepheid variables and type 1s and 2s and all that kind of stuff.
Yeah.
And that's totally reasonable. And the idea of who gets credit for measuring something is really funny, because, you know, is it the person who used the first viable technique? Is it the person who had the idea? Is it the person who refined it down to the point that people actually believe them? Is it the person with the clout so people actually believe them the first time? It's an interesting question.
Right. And not to mention, Hubble also ignored dust extinction.
Mm-hmm. The other thing you have to keep in mind is, you know, for the survey level student, most not going into science, sometimes simplification is better than.
Of course, yeah.
Yeah. That's the approach I took here, but I think a supplement would be awesome. And of course, me correcting anything that's blatantly wrong.
Sounds
Nice.
good.
Great
I
lab.
like it. Thanks so much, Dan.
My pleasure. Thank you for doing this semester, and hopefully we'll see a number of you next semester as well, or a second semester in one of the years once you've implemented.
And for my spring class, do I put that in the same Google Docs
I'll send out a
spreadsheet?
shortly. Once I get through the survey stuff, so probably mid-November, expect the same kind of let's start over, who's interested, and we'll get that all set up in December, and so you're ready to go by January or whenever your start date is.
Yeah, we're doing the 4-10 reversed in the spring, so we get 4 weeks, two 4 weeks in a row.
Okay.
Great, thanks.
Thank you.
Okay, bye.
Yeah, thanks, Dan.
Thanks, Dan.
My pleasure. Thank you, everyone.
Yep. Thank you. Bye.
Thank you, Dan.
Bye-bye.
See ya.
So Dan, for the spring quarter, I guess you'll set this up again separately, just for the
Yeah.
spring? Okay.
It'll be the same deal. There'll be a spreadsheet. You put in your information, and I'll create everything for you to make it easy.
Right, right. And you have to keep in mind, this would be my first time even trying it out for the first few labs. So, yeah,
hold
so
your hand.
I'll probably have a lot of questions for you initially, just in the logistics of setting it up in time.
Absolutely, and I'm happy to hold your hand through the process. If you're going to have TAs, they can. I may still have training sessions for TAs separate. Like this time, I merged them with the training sessions for you all.
Right.
I'll probably have the same TAs next semester, so I may not do it. But if there's demand from enough schools, I'm happy to train your TAs for you if it helps.
Okay, okay. Sounds good. I may have a different TA than the one I had this semester, so that may be useful, but I'll see. I'll let you know.
Okay.
Very good.
Good.
All right. Thank you so much.
Thank you.
All right. Bye. Hi, Dave. See ya.
Dave, how are you doing?
I'm hanging in there.
How bad is it?
Kind of hanging in there. I did have a couple of questions. One had to do with, I won't be implementing any of this until probably as early as summer next year,
Okay.
since I'm not teaching astronomy this spring.
You're welcome to pop in
And
next semester, but you don't have to.
well, and I probably will from time to time, but I was curious about, darn it, had it on the tip of my tongue. For like surveys that Rachel's been putting out. My class did the survey, the initial one, but are we going to be doing the after survey? Because they didn't do the labs, so.
Yes. Yeah. It's actually critical for the education researchers to collect background information. So that's why we didn't start everyone immediately. Also for their own personal logistical reasons, they weren't able to. But we want some people to start in the second year and some in the third year. And we're going to collect background information on how much did attitudes go up without Skynet, and then how much do attitudes go up with Skynet.
Okay, I just didn't want to bias any outcomes because we hadn't used any of the
No.
lab in any of that. So
No, that's taken care of in the instructor survey. We'll ask you which labs did you do, if any. And but that data is actually valuable and hard to come by since we have so many people who have already adopted. So that's helpful, very
Right.
helpful.
Okay.